All right, so here we are looking at chapter 9, part 2. So I hope that everything made sense with the theory and everything, but maybe it's just time to get the problem done, and that will help. So this is chapter 9, section 5. And we're doing hypothesis tests, but I want to give an overview to like the steps to hypothesis tests. So in these notes, it goes steps 1 through 6. I tend to write out step 0 through 6. And step 0 is the conditions, right? Everything we're doing from now on and the last couple chapters have been based on normality. So we got to make sure everything's normal and everything else is good. Step 1, we need to write out H naught and H1 or HA in this book. And that's just a statement of something that's already happening and then a statement of challenge, right? So something that's been accepted in the past, oh, in 2008, this was going on, or we assume this is true for now, and then challenge it. 2, we need to state alpha. That's the level of unusualness. I'm sure that was mentioned before, right? Probability of a type 1 error, level of unusualness. And that's just a cutoff when things are too weird and it's like, meh, I don't think I can really run with this anymore. I think things need to change. 3, we need to find a p-value. And just remember, that's a probability. When we plug this into our calculator, this is a probability of our sample. It's a little bit more complicated than that. And again, hopefully you picked that up in the previous notes. But basically, it's a probability that we could have gotten our sample. And then 4, if that probability is too low, we reject or not reject alpha. Right? So if not alpha, reject or not reject H naught. We found this probability under the premise, under the assumption H naught's true. We pretended, hey, H naught's true for a second. We ran the numbers. Oof, that's a low probability. So you're playing the odds. What are the odds? I'm just really, really unlucky, or was I lied to with this H naught? And then 5, you write a conclusion. And this is about H1, usually. Not usually, always, about H1. And you shouldn't say H1 necessarily, but it should be about the word version of H1. So let's get to it. We're talking about sigma unknown right now with one population, mean. I guess we should really note the mean. And to test hypothesis regarding population mean, we need to first make sure that the sample is obtained using a simple random sample. It needs to be random, and the sample values are independent. We tend not to write this down because this should be like auto. Like if you're ever doing anything with stats, it should be random. Things should be independent. Like we shouldn't even have to note that anymore. But some problems in MyOpenMath might actually ask you to do that. So first bit, check population is normal. So we've done this before. Either n needs to be greater than 30 or the population is given normal or no outliers in box plot. Then we write H naught and H1. Something I'll mention is in MyOpenMath, sometimes H naught looks a little funny, but in reality, this is what it should be. H naught is equal to some number that should be given. It's not from the sample, not from sample. So careful there. Locate the level of significance. So that's this part, that state alpha. Run t-test. Record the p-value right there. And then this important part. If p-value is less than alpha, reject. Right? If p-value is greater than alpha. Whoa, sorry. If p-value is greater than alpha, do not reject. Okay. And then we conclude our sentence by restating the alternate hypothesis. And you should start the sentence by saying, there is sufficient, I don't know why there's so little space. There is sufficient. Oh, I see what we were supposed to happen here. There is or there is not sufficient evidence. And another part I probably should have highlighted was this t-test. T-test. Okay, let's try it. Sorry, I was going a little fast there. Hopefully you caught all that. Well, we look at this problem and it says, hey, we got the RMR of healthy males is 5710. So right there, that's like the given, the assumed to be true. Researchers measure 45. So everything after this is about the sample, and found their mean to be this and the standard deviation to be that. Is there evidence? Here's some nice verbiage. Is there evidence to conclude the mean is different? So bottom line, I know H1 is going to be not equal to because it's different. I see step, the first bit, N is 45, which is greater than 30. That's my conditions, check. I know we're talking about mu because it said the mean, and just we're dealing with numbers and not percentages. Mu is going to be equal for us. For any Canvas problem, it's going to be equal. For any quiz problem, it's going to be equal. Every once in a while, MyOpenMath does something funky. And the assumed value, 5710, the starting value, 5710. We read through, we see alpha is 0.05. Right? I'm just following the steps that laid out in the notes just on the last page. This is step 0. This is step 1. This is step 2. Step 3 now, we're going to run a t-test. And I'll show us in the calculator. You know, this is something just like t-interval, or right, it's in the same place. Let me flip the camera. So you're in T, or you click stat, you went to tests and go to t-test. If you have raw data, like the next problem, we run the raw data. You got stats, mu, we say 5710. Right? Because that's what we said in H naught. X bar, for the data, the sample data, 57, sorry, 08.07. You can see then I got, or the standard deviation, 992.05. The N is 45. And the H1 or HA was not equal to. So I go calculate. And it spits me a p-value of 0.98, which I'll admit is an awkwardly large p-value, but it is what it is. It's a probability of 99%. So if H naught's true, the likeliness we got our data is about 99%. So H naught's probably true. P-value is 0.9896. So, you know, don't be afraid to press pause and go back and make sure you got that value. And this should be HA over here in step one. Okay, that's a very high probability. So what I would say is, since 0.9896 is not less than 0.05, it's not unusually small, we do not reject H naught. Which means step 5 here, we get to say there is not sufficient evidence to conclude the mean RMR, while listening to classical music is different. Normally, the topic or whatever H1 is not this long, but you get the idea. There's not sufficient evidence of H1 in words. And that's how that would go. And then honestly, it's rinse and repeat. Rinse and repeat, rinse and repeat. That's all that's going on. So let's look at it one more time. Let's look at this next example. Let's be a little bit more interesting. Instead of different, let's say above. And let's quickly run through this. So it says, hey, the US quarters weigh 5.67 grams on average. And we're wondering, hey, do state quarters weigh more? You know, hey, with the pictures, are things actually going a little bit different? Who knows? So we test it out. I look at this data and it's not greater than 30, but I can enter it in the calculator and note that there are no outliers in box plot. No problem there. And then H naught, HA, the stated value is mu is 5.67. And we think, hey, with all these pictures that are being drawn on these quarters, we think they weigh more now. Alpha is 0.05, no problem there. So now let's find this p-value. We're running a t-test. So this is why my camera hasn't switched back yet. So I first off, I have all this data in my L1. Wherever you entered the data, whatever list you entered it in, just remember that. Oh, I just deleted something. Oh, let's see. That was annoying. 5.7. Cool. So I go to tests, t-test. Since I have raw data, I'm entering the data input. It asks for the mu. That comes from H naught, 5.67, L1, and I think greater than now. Leave the frequency at 1. There's only like really special cases you'll change that frequency. And look at that p-value. Right? It's p, not p hat, not p anything else. It's just p, 0.0067. Which is pretty small. So since it's so small, we get to, my program is froze like usual. It's bound to happen once per video, right? So since 0.0067 is less than 0.05 by a lot, it's way smaller, we reject alpha. Or I'm sorry, H naught. I keep saying that. Then we conclude and get to say there is sufficient evidence there is sufficient evidence to conclude state quarters weigh more. More than 5.67. So that's that there. Yeah, and this isn't real data, by the way. I don't think state quarters actually weigh more, but it's just some like pretend data that we've made up. So that's how you test a mean, right? And we're going to run more and more hypothesis tests in this course. Right now, we're only focusing on 2 hypothesis tests, right? One about the mean, one about the proportion. So I really hope that's all making sense. Don't be afraid to send an email. We can always meet via Zoom on another time outside of Sunday. There's a couple caveats to hypothesis tests that aren't really going to affect us in this course, but in real life, I just want to mention. So when a large size is used in a hypothesis test, the results could be statistically significant, which means we reject, even though there's no, or the difference between the new mean and the old mean has no practical significance. Then we don't have to worry about this. Yeah, I guess practical significance. Again, practical significance refers to the idea that while small differences between statistic and parameter stated in the null hypothesis are statistically, who actually cares, basically? So for example, if you were to quickly read this problem, the idea says, hey, we think the age of first-time mothers is going up. So we say, hey, H naught mu is 25.2. We think this has gone up 25.2. We think it's greater than. But look at the X bar. The X bar is 25.5. And if you run through this, it turns out we reject H naught. But now let's think about this. 25.2 years compared to 25.5 years. Like, is that really concerning? Is that affecting things? Like, what is that? 2 months? The average age of first-time mothers has gone up 2 months in the last however many years, 20 years. Like, do I really care? No, not really. So just because you say something has gone up or something does go smaller, something is statistically significant, it may not be practically significant, right? Stats is very easily manipulated, which is unfortunate. Yeah. Don't worry about the classic method here. Something I'll mention though is when we run the t-test, we only care about the p-value. But MyOpenMath, for whatever reason, likes to ask about this thing called the test statistic, if you do things the old way. And it's there. The test statistic is the t. So maybe that's something we can write kind of at the top of this page. The test statistic. You never need to use it. It's a different strategy to running hypothesis test statistics. For a t-test, it's the t. And for a one prop z-test, which we're about to practice with, it is the z at the top. So just something to fill in to make sure you get the credit. It's hard to edit the problem, so yeah. Let's try this. This is chapter 9, section 5 again. I don't know why whoever created these notes separated them. My notes look a little bit different, but that's okay. But let's look at this. Let's look through this. We got one more example here, so stick with me. When results are unlikely under the assumption the null hypothesis is 2, we say the result is statistically significant. I think that has already been mentioned, but just in case it hasn't, it's okay. Whenever we reject, we say statistically significant. So if you hear that in some sort of news report, it's meaningful. Right? Again, we have these like low-key obvious things that need to be true. The sample is obtained by a simple random sample. Sample values are independent. Independent. But then it's the same process with a couple small changes. Population's normal. Well, that's going to be NPQ is greater than or equal to 10. That comes from H naught, just to be clear. You still got a H naught, and these are HA, A, in this book. You step 3 is still write down alpha. You run one prop z test. That's something that's different now. Something else we should just real quick note. It's P instead of mu. It's an easy thing to get wrong. So P instead of mu. This reminds us, this just explain what a p-value is. Remember that it is a probability. If we're less than, then we reject. If we're greater than alpha, then we don't reject. And we say there is or there is not. And it should be sufficient evidence. That goes in there, sufficient. Yeah, check that out. Okay. Let's just do one of these example. We don't need to do the other ones. We'll just do this top one because with one prop z test, it's the same thing over and over and over. Which one do we do? We'll do the first one here. So in 1997, 46% of Americans said they do not trust the media when it comes to reporting accurately and fairly. 2007, we asked 10,010 people, or 1,010 people, 525 said they don't trust media. Is this enough evidence to say that this percentage has increased? Right. So you can see N is 10,010, P is 0.46. So we run this MPQ, 10,010, 0.46, 0.54. You can put that in your calculator, but it's pretty clear to see that it's going to be greater than or equal to 10. I guess I can just run it real fast. 1010 times 0.46 times 0.54. 250. Way bigger. Check. Then we go to the next step. H naught HA is equal to 0.46, and we think things have gone up. We think the distrust has gone up. P is greater than 0.46. We say at alpha 0.05. It's usually 0.05. And then we run a one prop z-test. And we'll do that together. And these, I always thought looked a little bit smoother. You go stat, tests, one prop z-test, and it asks you, well, my data happens to already be entered. 0.46, that comes from H naught. That's that P right there. The X is the number of people that said yes or think a certain way or agree with something. And then N's the people you asked. We're wondering if it increased. Then you go calculate. So a couple things here. This Z, that's the test statistic. So if you're asked about test statistic, make sure you enter that. There's a P hat, but that's not the P value. The P value is here, 6.85. That should sound weird. Remember, P value is a probability. Probabilities cannot be above 1. So you look at this, E to the -5. That's that scientific notation that you might have learned in your chemistry class. That was really, really annoying. But what it means is move the decimal left 5 places. So what we get is a p-value of 0.00069. Very, very small, but very common. Like, don't think that's a weird answer. If you 0.98 that we got earlier, that's a weird answer. This very small p-value, extremely common. But anyways, so we finished this problem off. We're saying since 0.00069 is less than 0.05, we reject H naught. Which we then get to say there is sufficient evidence of H1, which is basically saying there is sufficient evidence to conclude that mistrust in the media has increased. Since 1997. And that is hypothesis tests. So work with each other to really get this process down. 9.5 does as good homework examples in MyOpenMath. So really look to those and see what's going on there. Use your instructor, but ultimately, I hope this all made sense. Again, reach out. You know, I'm open to extra office hours if needed, especially for this chapter. It's an important chapter, but I'm around every Sunday. So, other than that, until next time.